Welcome to a video on section 2.2 regarding limits involving infinity. So this section will cover both the limit of f of x as x approaches plus or minus infinity and the limit of f of x as x approaches c, and the outcome is plus or minus infinity. Just to kind of give you an idea of what's going to happen. When we experience this kind of limit, they'll give rise to a horizontal asymptote. When we experience this kind of limit, they'll give rise to a vertical asymptote. And we're going to explore that in this section. So let's start with what we call finite limits, meaning that the limit is a number, not infinity, but x will be approaching plus or minus infinity. So what this means is that we're going towards the ends of the graph. And you guys did spend some time talking about horizontal asymptotes in Algebra 2 and pre-calculus. So the line y equals b is a horizontal asymptote of the graph of a function f if either one of these two things happens. As x approaches infinity, you're going towards a line, or x approaching negative infinity, you're also going towards a line, or both. So let's explore 1 over x. Obviously, if you make a quick table, I know I can't plug in 0 because 0 is undefined. If I do plug in 1, I get 1. Plug in negative 1, I get negative 1. Plug in 2, I get half. Plug in negative 2, I get negative half. If you plug in even larger numbers like 10 or 100, y just gets closer and closer to 0. So the graph looks like this. And you guys learned that there would be a horizontal asymptote, but the misconception with horizontal asymptotes, people think that you can't cross horizontal asymptotes, and that's not true. You actually could cross horizontal asymptotes. The whole point of a horizontal asymptote is to examine how the left end, which is when x is approaching negative infinity, and the right end, which is when x is approaching positive infinity. So examine how the left and right end of the graph behave, how both those behave. So in this case, obviously as x approaches negative infinity, we do see from the graph, and we can examine numerically, if you plug in like negative 1,000, negative 1,000,000, whatever, it's approaching 0. On the other side, it's also approaching 0. I apologize for a little disruption. The cat here keeps meowing. Hopefully she'll stop. Okay, we'll keep going. So what this tells us in the starburst is that the limit as x approaches plus or minus infinity of 1 over x equals 0. That's an important limit that we'll have to utilize throughout this course. Let's investigate horizontal asymptotes for other types of functions. What if you have a constant function like f of x equals 3? Well, if f of x equals 3, that's just a horizontal line that crosses the y-axis at, of course, 3. So regardless if I'm going towards positive infinity or negative infinity, the limit's just going to be 3. So you could think of a constant function having horizontal asymptotes, because that's the whole point, is examine how the left and right ends behave. It's not a boundary you can't cross. That's a total misconception that sometimes, I don't say this taught wrong in Algebra 2, I don't know how to teach it differently sometimes, because you're not ready yet to learn about limits in Algebra 2. But I could see why people would misconstrue that, because you learn about vertical asymptotes in which you can't cross. So it's kind of a tricky thing sometimes to teach, but when you get to calculus, the hope is that it starts making more sense because you know about limits. And because we have a limit explanation, you can see that it's just all about left and right hand behavior. It's not about a boundary you can't cross. So in this case, the limit as x approaches positive plus or minus infinity of k, where k is a constant, is just going to be the constant itself. Because as I go anywhere, if I go all the way to the left here, y is approaching 3, or y is 3 basically, if I'm going towards infinity, and likewise on the other side. Okay, let me go ahead and clear the screen. So let's look at some other types of limits. What if we're doing sine x over x? Now, in the 2.1 video, the last couple pages, we talked about when x approached 0 of sine x over x, the limit was just 1. Or we had sine kx over x, it was going to be k. That was in 2.1, we talked about this. However, don't confuse this when x is approaching negative infinity or positive infinity. Now, the graph of sine x over x, if you were to do this in Desmos or your TI-84 calculator, will look kind of like this. And it ultimately just kind of does this oscillation off to the right. If you were to plug in numbers, like negative 100, negative 1,000, negative 10,000, so we're going towards negative infinity here, or here we're going towards, positive infinity. You get negative 0.0051 or negative 0.000826, negative 0.000300. I'm just looking at my other screen here. And then, of course, we'll see something kind of similar over here, negative 0.005. I'm just going to give some approximations. I think in this case it's positive 0.0826. Or maybe it's positive here. I'm not 100% sure. I'm not actually punching these in. I'm just copying it from somewhere. Or is it like negative 0.03? The bottom line is that these are getting closer to 0, or they're roughly 0. Now, yes, there is an oscillation. Sometimes y is positive, sometimes y is negative. However, the whole point, does y approach something? And it does. The answer is yes. And what is y approaching in each of these cases here? Each time it's approaching 0. So we investigate this numerically and graphically. So the fact illustrates that a function's graph can cross the horizontal asymptote. That's totally okay. It's all about approach. It's all about, does y get closer and closer to a certain number? So basically, this is what we're trying to answer. Does y get closer to a finite number as x approaches positive or negative infinity? That's what we're trying to answer here. And if you do, if yes, you have a horizontal asymptote. So that's the other thing in the starburst here. We have another limit we can work with now. But it is different than this one, right? Just keep that in mind. So try to always think about these graphically or numerically if you can. Okay. So let me go ahead and clear the screen. Let's move on to page 2. And we are going to go up to 4 pages, but I'm going to probably stop this video after page 2 because it might be a little much to watch. You might want to do some parts to watch, 4 pages of notes. Plus, I think I'm going to have to feed the cat soon. You can see the cat's on the top of the washer there. So anyway, use a graph and table to find the following. Okay, that one's kind of a funky one. If we graph this in Desmos, you'll get something that looks kind of like this. It's kind of interesting. Y equals 2, and y equals negative 2. you are going to notice that this graph kind of levels off as x goes forever towards the right, or as the graph goes forever to the left. That y is approaching 2 or -2 in those directions. So, obviously we could just state our answers here. And you can make a table if you want. You could plug in like -1,000 or +1,000 and see what happens. But what this illustrates is that you could have 2 horizontal asymptotes. That's also a possibility. And of course, our y equals -2 and y equals 2. You might remember logistic functions from pre-calculus. Logistic functions kind of look like this. They're kind of like exponential in nature, but they kind of taper off. So, that's a possibility. So, limits as x approaches plus or minus infinity have similar properties to those that we met for limits as x approaches c. So remember the property we talked about in 2.1. As x approaches c, and we had these 2 different limits here for 2 different functions. And then we could add the limits, we could subtract the limits, whatnot. Same thing if x is approaching infinity or -infinity. If you know what those limits are for 2 individual functions, but then you're combining those functions by addition or subtraction, multiplication, division, you could just combine the limits in the same kind of way. So in this case, you could do L plus M, L minus M. Looks like I need to feed the cat soon. So once I finish page 2, I'll pause this and or stop the video and start a new one. K times L. Right now is actually a good time for me to do this because the rest of the house is sleeping. So, except for the cat. So f of x or g of x is L over m. This is L raised to r over s power. Mind you, for this one, you can't have m equals 0. So the limit of g of x is x approaching infinity if it equals m, assuming m is not 0, because otherwise then you have a problem there. And of course the power rule, you have that. And there's some conditions, we don't assume that s could equal 0 because it's a denominator of the fractional exponent. But anyway, yeah, you can use these limit properties even if x approaching infinity or -infinity. Now, another thing that we might want to just discuss, I'm looking at my annotations here. Could you have 3 horizontal asymptotes? Since, we could have 2, why not 3? Well, the answer is no. Because remember, it's all about this, the limit as x approaches -infinity of f of x, and the limit as x approaches +infinity of f of x. Now, typically, these might both equal the same number, L and L. Sometimes they could equal different numbers, as we saw in example 4. But you can only get one limit from each side. So, no, you can, again, only get one limit from each side. Because that's the whole point of horizontal asymptotes. It's about x approaching +infinity, which is one option, or -infinity, which is another option. Again, sometimes they're the same, sometimes they're different. But you're not going to have 3 horizontal asymptotes. So sometimes you might see multiple choice questions on like standardized tests that might put that as a choice to kind of throw you off a little bit. You can't. It's impossible. It's all about the end behavior. To be honest with you, HA, sometimes I like to just call EBA, end behavior asymptote. So let's look at exam 5, talk about those, and then I'll stop the video and start a new one after that. Clear? Let's move down. So now here's the one thing about these limit theorems, however. The limit theorems assume that we actually have a finite limit, right? Like, you know, the limit as x approaches infinity of f(x) equals some number. Likewise for g of x. But what if those limits did not exist necessarily? That is, they're not finite real numbers. So what if L and M? We probably can't necessarily use these rules. So let me give you a good example. So look at how C combines sine squared plus cosine squared, or D does 2 sine squared x plus cosine squared x. So C and D are combinations of A and B. Let's go on with A and B first. If you do limit of sine squared x, remember sine squared x is sine x then squared if you put that in Desmos or the calculator. If you were to graph that, it's going to look kind of like this. Actually, it's kind of sloppy. I can do better than that. Okay, not the greatest, but that's sort of how it looks. Nope, I was wrong. Starts with the origin. Okay, take 3. You are squaring, so the output's always positive. Cosine starts at 0, 1. I should know that. You're squaring, so the y values are all positive. So the limit won't exist here as x approaches infinity for either one, because I really don't know. I mean, for A and B, for sine squared x and cosine squared x, y oscillates between 0 and 1. So I really don't know what it's going to converge to. However, if I were to graph this, hopefully you recognize that that's just equals 1. That's a trig identity. It's a very famous one, the Pythagorean trig identity. Sine squared plus cosine squared equals 1. So the course limit does exist here, and the limit A equals 1. So it's weird because the individual limit did not exist. So one would think the combination would also not exist, but it does exist. It equals 1. So it does exist. But then this one's kind of weird because this one does something kind of funky like this here. I mean, yes, it's going to be sine squared x plus another sine squared x plus cosine squared x. So it's sine squared x plus 1, which is really just like this up here with a shift of 1 up. So actually it's not as funky as we think. It's just taking A and shifting it by 1. The course limit here won't exist because it's oscillating. So the limit theorems above only hold true if L and M do exist. If the limits of the individual functions exist, then you can then you can add, subtract them. But if they don't, then when you combine two limits that have a D&E result, we're not really sure what's going to happen when we combine them. You just have to take it case by case. So just be mindful that the limit properties above are only going to hold true if the individual limits exist. So limit theorems above only hold true if the individual limits exist. Otherwise, you really don't know. And just you have to handle by case like we saw in example 5. Okay, so I'll go ahead and stop this recording and I'll start a new one.